So based on the title and abstract, you might think I'm an observer, but I'm still mostly a theorist. And when I meet observers, I like to ask them for their wish list. I want to know what they're thinking about, what they wish to understand about the things they see, and if I can help them explain what they're seeing. Unfortunately, I don't always get a good answer from the observers. And today, I'm putting on my good observer hat. I want to be a good observer to you, and I want to share with you my observer's wish list. I want to tell you about some of the mysterious and interesting and or confusing phenomena that I'm observing in the real universe. And I want to invite all of you to help me understand what's going on. Okay, and before I start my talk, I want to first give an advertisement about my student, wonderful student Chongha's visit next week. And he's going to talk about this really amazing set of numerical simulations he did following the accretion flow from galaxy scales. This is based on M87. From galaxy scales all the way down to about 10 spatial radii, covering about 8 orders of magnitude in the dynamical range. And so he's really, really wonderful. I hope, I mean, he was a pre-doc fellow here, so some of you probably have met him, but talk to him again if you have already talked to him. Every time you meet him, he's probably done more things. And if you have not met Chong, please, he's really, really wonderful. Okay, so in my talk today, I will be focusing on turbulence, or mostly things related to turbulence. And I'll be talking about turbulence first in the interstellar medium. And I want to tell you about how we can actually use young stars as a tracer of the ISM turbulence. And then I will talk about turbulence in the intracluster medium inside galaxy clusters. And I'll talk about how we can use cool clouds as the tracer of the hot plasma. And if we apply that to cluster centers, we can have a better understanding of how AGN feedback operates. And if we apply that to cluster outskirts, we can actually probe the plasma properties below the mean Coulomb mean free path. Okay. So turbulence is really everywhere around us. The air is turbulent. You might not see it. I mean, we don't see it because we can't see the air molecules. And we only see the turbulence when there are tracers in the air. And that's when you know, okay, it is indeed turbulent.
Sorry, just keep going.
I'm not talking about black holes today. Wait, what's that?
Okay, great. Now
oh, that's my student. Oh, wow. How did he get the link? Oh, hi, Roy. And so a lot of the work I will be telling you about today has something to do with finding a good tracer in the universe to help us study turbulence in different environments. And here's another example of using a tracer of your turbulent flow in your coffee when you pour milk into your coffee. And if I ask you what is turbulence, many of you will probably give different answers or slightly different answers, but I think we can all agree that a turbulent flow has a lot of eddies or whirls or swirls or twirls of different sizes. And as is described in this beautiful poem, big whirls have little whirls that feed on their velocity, and little whirls have lesser whirls, and so on to viscosity. And unfortunately, we still do not have a full mathematical description of turbulence, which is why we're still studying it. But we have done a lot of experiments so that we understand when turbulence can develop. And it's largely dependent on the so-called Reynolds number, which is simply the characteristics size of the system multiplied by the characteristic velocity of the system divided by viscosity. And when this Reynolds number is large, typically larger than 100, then the flow tends to develop turbulence. And we also have a pretty good understanding of the statistics of a steady state incompressible turbulent flow. And you probably, most of you have heard of the Kolmogorov power spectrum. And that is describing kinetic power energy as a function of K in a steady state incompressible turbulent flow. And you inject energy into the system at some small K or large L, large size. The energy cascades down to smaller and smaller scales, big whirls turning into little whirls, all the way down to the dissipation scale. And between the injection scale and the dissipation scale, EK is related to K with this beautiful power law of minus 5/3. So, and we can easily derive this using energy conservation and dimensionless analysis. And so the relation between EK and K is directly related to the relation between velocity and size, because kinetic energy is velocity squared, and that's 1/L. And this pretty much is equivalent to a size velocity relation that's V proportional to L to the 1/3, meaning bigger eddies move faster, smaller eddies move more slowly with this kind of relation. And for the most of my talk today, I will be using this velocity size relation. One way to think about it, it's a poor man's power spectrum, but it's more or less equivalent to the power spectrum. Okay. And I also want to emphasize again that turbulence is everywhere in the universe, whether you see it or not, just like it's here in the air. So I will be talking about turbulence in the interstellar medium and the intracluster medium. And I'm hoping, even if you work in other fields, what I talk about today can be somewhat useful or helpful in your thinking about what you're working on. Okay, so I'll start with the ISM turbulence. When we think about the interstellar medium, we usually picture some pretty clouds. And this is the clouds in the Orion star forming region. That's the Orion constellation, possibly the only constellation you can see in New York. And in case you didn't know, it's a star forming region there. And if we look at the stars in there, they look like, when I showed this to an artist, they said, wow, they look like little fish swimming in the ocean. And I do think in some ways stars are like little fish swimming in the turbulent ISM ocean. And a few years ago, I asked this question, well, we know that stars are born out of turbulent ISM. If we were to look at very, very young stars, wouldn't they remember the kinematic, the turbulent kinematics of their natal clouds? And if so, can we use stars as tracers of ISM turbulence? And there is a unique strength of using stars to measure turbulence. When we look at gas, we only have access to very much projected information. We only know its line of sight velocity. We don't know how gas moves across the plane of the sky. We know where gas is located in the projected plane of the sky, but it's really hard to figure out where the clouds are along the line of sight, the distance to the clouds. With stars, when you combine Gaia and APOGEE surveys, you actually have full access to the full 6-dimensional information of many, many stars in the Milky Way. You know their three-dimensional positions and three-dimensional velocities. So potentially we could study turbulence for the first time in the ISM with no projection effect whatsoever. And so a few years ago, my wonderful graduate student had the same person, okay, who also did the amazing simulations, did this observational project with me as his first project, which he finished in 3 months. I still can't believe it. So Chong looked at the stars in the Orion complex. He carefully selected a subset of stars that were really, really well observed. These are all very young stars, and they were sorted into separate groups using machine learning algorithm. And we computed the first order velocity structure functions of these stars. And what that is it's basically a 2-point correlation function that measures the relation between mean velocity difference as a function of the pair separation. So it's basically the velocity size relation that I mentioned earlier that could directly translate to a power spectrum. Okay. And so as I mentioned earlier, for a Kolmogorov turbulence, you would expect a structure function with a slope of 1/3. And for the majority of the stellar groups we looked at, we saw something that more or less had that slope. And this blue line is the Larson's relation that was measured for the molecular clouds in the Milky Way. And you can see that the structure functions of young stars more or less follow Larson's relation. And to us, that means we are indeed seeing the memory of turbulence in these young stars. And there's one exception, which is this ONC, the Orion something N cluster, the Orion
Nebula cluster.
Thank you, Mordecai.
The voice from
Your lifeline.
Thank you for saving me. It's been a few years. I forgot. I'm sorry. Anyways, it's a star cluster where.
Is it older?
No, but it's denser. So the gravitational interactions between the stars have had a chance to erase the memory of turbulence. So then you see more or less a flat structure function. And if we look at the structure function of all the Orion stars put together in more detail on very small scales, unfortunately, there's contamination from small scale dynamical relaxations and binary stars that we just don't know how to remove. You always have a little bit of a noise here, unfortunately. But we do recover a little bit of a nice turbulence inertial range. That's that beautiful little parallel that tells us, yes, turbulence. And what's really cool is we can also see the little bump there that indicates energy injection into the system. And for Orion, this bump actually nicely corresponds to what you would expect from a supernova explosion that happened a few million years ago. And there was other supporting evidence pointing at that supernova explosion. So in a way, perhaps it was the first time that we're seeing supernova energy injection into ISM turbulence in the memory of stars. And then the next year, we looked at more star-forming regions and confirmed, yes, we see this more or less universal turbulence in all the Milky Way star-forming regions we looked at. And they're all more or less consistent with Larson's relation. And in this paper, we also compared the structural functions of the stars and those of the warm ionized gas. And in some of the regions, especially those with recent supernova explosions, we also saw evidence of energy injection preferentially going into the warm ionized phase, which I thought was also kind of interesting. And then earlier this year, another wonderful student worked with me and did a more comprehensive study using more updated data from Gaia 3. So this is Ben Balgus, who was a post-bac fellow with me and has recently started grad school at Dartmouth College. So Ben revisited these stellar groups using the new Gaia 3 data. So now we have more stars. And we looked at the anisotropy of turbulence. As I mentioned earlier, with gas, you only have access to the projected information. And with stars, we have 6-dimensional information, so we can see, is turbulence isotropic in the ISM? And I'd say for the most part, so you're supposed to be comparing the blue, purple, and green lines for the different regions. And you can see, for the most part, they're pretty similar. There are regions where these lines are well separated. So we sort of called it mild anisotropy of turbulence in the ISM. So it's not really strong anisotropy, but it's also not completely isotropic. What that tells us is, well, in a perfect Kolmogorov turbulent flow, you would expect perfect isotropy. So any deviation from that tells us there's something else going on. And we already know the universe is complicated. There are more things going on. And I'll mention one of the things, magnetic fields. So well, through Planck, and there were other methods, we could measure the magnetic fields in the projected plane of the sky. So we don't have the 3D field information, but we know the orientation of the field lines in the projected plane of the sky. So we asked the question, what stars know about magnetic fields, or what magnetic fields know about stars? We looked at the alignment between the stellar motions and the magnetic field directions. I'm gonna give you a test now. No, not quiz, no. What's your prediction? Do you think stars, young stars, should move preferentially along the field lines or perpendicular to the field lines? Or do you think they should just not care about the field lines? Does anybody? You're all good theorists. It's time to prove you right. Who wants to make a prediction?
They shouldn't care that much, right? Because we know that most GMCs are. Mordecai, of course, has an opinion.
Yes. So this is the scale where we do not expect magnetic fields to be dynamically important. Mordecai, that's your prediction too?
Yep. Okay.
Awesome. Anybody else wants to make a different prediction?
I bet we're going to be wrong though. Because otherwise you wouldn't have asked the question.
Well, but this is my wish list, okay? I don't know why, but we detected, and Ben even did like a MC whatever analysis to prove that it's not consistent with random. But obviously, this yellowish line shows that the magnetic fields in Perseus are preferentially perpendicular to the stellar motion. I don't think anybody had ever made that prediction, and I have no idea how to explain it. I would like to know what Mordecai thinks, but as a theorist, I felt obligated to throw in some theoretical explanation. I love that. Thank you, Mark. So I'll give you my very hand-wavy, terrible explanation that we put in the paper, and you can tell me that I'm wrong. But yes, please help me think about it. So my really hand-wavy explanation was, well, you have the hierarchical collapsing of clouds, So first you form a sheet, right? And when you form the sheet, the magnetic fields will be mostly perpendicular to the sheet, as is suggested by this observational paper. And then you form stars within the sheet. So then the motions of the stars will be mostly along the sheet and therefore perpendicular to the magnetic fields. It's very hand wavy. And also that picture is for Taurus where we didn't see. So yeah, help me theorists. And those of you who have simulations of star formation, please let me know if you see this in your simulations, because I've never worked on star formation simulations. I'm so curious what you see. If this is just a coincidence, I don't think it is. How can you make that a coincidence? And like, why do you see it? If so, why? If not, why? Help me. All right, and Mordecai, help me. Okay. So I'm gonna move on to galaxy clusters. Okay. So for those of you who don't think about galaxy clusters on a daily basis, here's a movie put together by the TNG team showing you sort of the evolution of a galaxy cluster in our TNG simulation. So as you can see, the lifetime of a galaxy cluster goes through many, many merger events. I like to think about galaxy clusters as cosmic trash cans. Everything falls in, not a lot comes out. And there's a lot going on. I think towards the end of the movie, the color will switch to the stellar component or the galaxies in the galaxy clusters. But the majority of the mass is actually in the dark matter inside the galaxy cluster. They're mostly held together by the dark matter. And the majority of the baryons are not in the stars either. They exist in the form of very hot and diffuse gas or plasma called the intracluster medium. It's this blue stuff. And hopefully you wouldn't be surprised that with all the mergers going on, there's turbulence driven by these structure formation processes. And simulations have typically produced a few up to 20% of turbulent pressure support in galaxy clusters. And turbulence is a very important astrophysical process inside a galaxy cluster because turbulence can amplify magnetic fields. It also accelerates relativistic particles to give you these pretty structures that I will not be talking about today, but I'm totally fascinated by. These are structures detected in the radio band. So these are synchrotron emissions from relativistic particles, likely accelerated by turbulence. And as I mentioned earlier, turbulence can be driven by structural formation in the bulk of the ICM. And then in the centers, there's also black hole feedback that can potentially drive turbulence. In galaxy clusters, turbulence is also of interest to physicists because another way to think about the ICM is that it's a giant plasma lab that we cannot recreate on this planet. It's a very special plasma because it's so diffuse. The Coulomb mean free path can be ginormous. In cluster centers, it's typically on the order of 10 parsec. In cluster outskirts, the Coulomb mean free path can be on the order of 10 kiloparsec. That is the size of a galaxy. And so it's really time to think about viscosity and at a more fundamental level, the collisionality of this plasma and also your fluid assumption that you make before you run any hydrodynamic simulation. And as this recent paper has shown, even if you just assume some really simplistic Spitzer viscosity in your plasma, you produce very different structures in your simulated galaxy cluster. And yet this has been largely ignored by the cluster, well, actually not class, but the galaxy formation evolution community. And of course, viscosity in this environment is more complicated than that because it's this weird plasma, it's weakly collisional, weakly magnetized, subsonic, superalfanic. I'm not going to explain all of these lines. This is sort of the theoretical expectation of what the cascade of turbulence might look like in this plasma. I'll just sort of briefly mention that if we think this plasma behaves somewhat similar to the solar wind plasma, then we might see a difference in the cascade and dissipation of different MHD modes. The more compressive modes should dissipate more quickly on larger scales, like this one. And on smaller scales, maybe we should only be looking at mostly alphanic turbulence. And as I will show you today, observations now, if we use cool gases tracers, can probe these scales in cluster centers and cluster outskirts. So we are observationally probing potentially this transition between partial dissipation to the alphanic turbulence. And again, state-of-the-art simulations are resolving these scales. And so we really should be thinking about how we can properly model viscosity in these environments. But before I talk about viscosity, I'll talk about cluster centers first. And because that's related to something that's really dear and near to my heart, black hole feedback. One of the ideas that was really attractive was, well, so first, we all want to know how black hole feedback operates. We all know that black holes are feeding back, but how does the energy from the jets, in this case, we're talking about low luminosity black holes. I mean, it applies to quasars too, but we can talk about that later. So we all want to know how the energy from black hole jets gets coupled to the host galaxy or galaxy cluster, right? And one attractive idea is maybe the jets can drive turbulence, and then the dissipation of turbulence will generate heat, which can suppress radiative cooling. So a few years ago, I guess that's many years ago now, a bunch of us that worked on simulations of black hole feedback tried to look at our simulations to understand what was doing the heating, what was doing the feedback in our simulations. And we all had slightly different models, we had different analysis methods, slightly different conclusions, but overall, we all agreed that there wasn't much turbulence. And shock waves, sound waves, adiabatic processes, mixing, those are all more important than the dissipation of turbulence in the simulations. On the other hand, the X-ray observers have figured out smart ways of extracting information from the very limited X-ray data. So here's a picture, Chandra X-ray picture of the central region of nearby galaxy cluster called the Perseus galaxy cluster. And you can see there's fluctuations in that image. And the observer said, well, if we can translate the surface brightness fluctuations to a density fluctuation, and then translate that to a velocity fluctuation, then we can infer a level of turbulence. And then we can infer a level of turbulent heating. And the inferred level of turbulent heating can perfectly balance radiative cooling in two nearby galaxy clusters. And you can say, wow, there are so many assumptions going into that. I don't believe you. Very quickly, it was confirmed by a more direct measurement of the velocities of the hot plasma. So this was by, back then that was Hitomi. So Hitomi was a X-ray telescope that had exquisite spectral resolution. It tragically died after it made one observation. And that one observation was looking at the central region of Perseus. And what Hitomi told us is within this big region, along the line of sight, there is a non-thermal line broadening that would translate to a velocity dispersion of 100-something kilometers per second. And that's exactly consistent with what the Chandra surface brightness fluctuations suggested. So it seems, and then later, CRISM confirmed this sort of result. So it seems that the observations are converged to the same conclusion that says turbulent heating is important. Models, on the other hand, are converged that says turbulence is not important. And as all of you will agree with me, when the observations do not agree with the theoretical models, there must be something wrong with the observations. Okay, what can be wrong with the observations? As it turned out, the X-ray observations are just very limited by the sheer amount of photons they receive, which effectively limits their spatial and spectral resolution. That's my understanding, but good thing is there's no observers here. Nobody can correct me. But what I know for sure is if we want good spatial and spectral resolution, we want to use optical or radio observations. And luckily for us, the centers of galaxy clusters are oftentimes multi-phase. So this is, again, the central region of the Perseus cluster. And on top of this X-ray background, I'm plotting the H alpha gas that you can observe using a ground-based optical telescope. So that gas is probing about 10 to the 4th Kelvin. So depending on who you ask, it's warm gas or it's cool gas. I'm going to call it cool gas because the background is 10 to the 7th, 10 to the 8th Kelvin. Okay. So you can ask, how do you even have these cool filaments there? Well, many of us have asked that question. It's still kind of debatable, but a lot of the simulations, including my own, suggest that these could have cooled out of the hot plasma due to thermal instabilities. And in my simulations, they were actually directly triggered by the feedback from the black hole. Now, regardless of how they formed in the first place, they could still be kinematically coupled to the hot plasma through hydrodynamic interactions and also magnetic fields. And so what I thought about doing a few years ago was maybe I could look at how these cool filaments are moving to understand how the hot plasma is moving, just like we can look at how the leaves are moving to understand how the wind is blowing. And with these IVU telescopes, you can actually get the line of sight velocities of these cool clouds. And so I pulled out the tool that one tool I know how to use. I computed the first order velocity structure function of these filaments. And as you can see, there's a beautiful parallel there on small scales that suggests big worlds are turning into little worlds, right? And we also see these bumps indicating energy injection. And if we look at the inner filaments that follow a structural function shown in red, it reviews this energy injection around 10 kiloparsec. And that's exactly the size of these X-ray bubbles that are still filled with radio emitting plasma that were created by the jets from the black hole. So somehow these filaments know what the black hole is doing. It's kind of crazy. And if we look at the outer filaments, they follow structure function shown in green, and they review another energy injection scale that corresponds to this older bubble. So it seems that these outer filaments are feeling the motion driven by a previous outburst from the black hole. So we thought we not only detected turbulence driven by black hole activity, we not only detected turbulence, we also detected turbulence driven by the activity of the black hole. And the first thing I did was, well, I checked my assumption, right? Are these really like leaves flying in the wind? So we compared the optical measurements with the X-ray measurements. So these two horizontal lines represent the Hitomi results. So Hitomi doesn't have good spatial resolution. So the results are just represented with these horizontal lines. There's no spatial information, but you can see there's good agreement in terms of the amplitude between the X-ray and the optical measurements. And that purple line is the surface brightness fluctuation analysis using the Chandra X-ray data done for a region tailored to match where the outer filaments are. And they're more or less a perfect match. So purple and green agree really nicely. So at least within the range that both optical and X-ray are probing, it seems that the hot phase and the cool phase are really well coupled kinematically. Is the coupling still good on smaller scales? We don't know. Maybe future X-ray telescopes can help push this further, but it's actually, what I heard is it's going to be impossible to push it all the way down to this scale. So it's up to theorists to figure out to the best we can how good this coupling can be, or to what extent. So for now, I'm just going to assume the coupling is going to be good-ish. So I can talk about plasmas and other things. But before I talk about plasmas, one thing I noticed was, so first I looked at 3 clusters. So that's Perseus, and I looked at 2 more because I had observer collaborators. They said you can never publish a paper with just like one thing. And why don't you look at 2 more? And at first I said, no, 1 is enough. They're all the same. It turned out they're not the same, okay? I'm so glad I looked at 2 more. They all showed different slopes in their structure functions. They all look like power laws, and yet they all have different slopes. And they're all way steeper than Kolmogorov. So why are we not seeing Kolmogorov there? I don't know. I don't think anybody knows. There were a bunch of sort of hand-wavy theoretical explanations proposed. I won't talk about the ones I don't like. I'll talk about the 2 that I like. So my favorite explanation is still just simply, we're not detecting the cascade of turbulence. I'm afraid that black holes are terrible drivers of turbulence. They're just not driving a lot of turbulence, and what we're detecting is the signal dominated by the bad driver itself.
Like the bulk motions.
Exactly.
That's what I was just wondering. I was like, how do
I know.
disentangle the bulk
I agree.
motion? Because we know there's a huge flow.
That's what I'm saying. People don't like it. I'm like, I get it. I'm a bad driver myself. So, but there is another pretty attractive idea, which I want to briefly mention, which is what the solar wind people have been telling me. They think we might also be detecting some partial dissipation of the compressive modes. And this is the right scale to see that, if that is happening. And I don't know how we can test it. So again, help me. I have some ideas I'd like to check for. So we don't know what, also, if it's bulk flow, you would expect to see some Kolmogorov on the very small scales.
Yeah.
Why are we not seeing that, right?
Can you resolve that scale?
Great question. Well, so the answer to any question you ask an observer is more data.
Of course.
Of course. And luckily for me, my observer collaborators already had more data. And so we just analyzed more data later on. And so for the most part, these structure functions of the other clusters look kind of just like the ones I've seen. You have a parallel with some slope that's, steeper than Kolmogorov. We don't know why. But one thing I want to mention is it does have an interesting implication in terms of turbulent heating, right? So previously, the X-ray observers were inferring the level of turbulent heating based on the measurements here, because that's all they can probe. And if you were to extrapolate the amount of heating, you would use a Kolmogorov cascade and get a decent amount of heating, right? What we see is actually at small scales, the amount of turbulent kinetic energy is way smaller than what you would extrapolate just based on Kolmogorov cascade because the slopes are steeper. And so every vertical line here is for one cluster. And so if you were to use the X-ray information, or more or less what the X-ray observers would detect, you would conclude that, oh, turbulent dissipation can more or less balance radiative cooling in these systems. And that's exactly what the X-ray people have been saying. But if we could resolve the small scale kinematics, the amount of turbulent dissipation is on the order of a few percent of what you need to balance cooling. So that's pathetic level. And that's exactly what simulations have found. So, right, if it agrees with my simulations, it must be right. So what about the missing Kolmogorov? I think we found it in one system with this really, really long H alpha tail. And if we look at the structure function of the outer filaments, that's shown in green, I think we see a pretty convincing break. And I think we're seeing the transition between crazy driver's behavior, which gives you a steep slope, to the underlying cascade, which is what you would expect from physics. That's what I think is happening. Not everybody is convinced. And I also think we recently detected it in M87. So we got some ALMA data for this teeny tiny little blob there. And if you look at the structure function shown in purple, you see a similar transition from a steep slope to this more flat Kolmogorov-like slope. So the key is to either go to small scales or to move away from the black hole, so your signal is not dominated by the driver. And you can move further away from the black hole all the way to cluster outskirts. And you see multi-phase gas there in the tails of jellyfish galaxies, which Stephanie is an expert on. So this is one jellyfish galaxy called ESO 137-0001. As you can see, the tail is multi-phase. So what are jellyfish galaxies? These are galaxies that are moving really fast through galaxy clusters, through the ICM. They're moving fast because the potential well is so deep. Typically, they're moving at like 1,000 kilometers per second. From their perspective, the hot plasma acts like a wind that's blowing onto the galaxy. And that wind, the ramp pressure from the wind, strips the gas to form a tail. And here is a lab experiment demonstrating that process. Okay. And the tail, as you can see, is also multi-phase. You observe the tail in all different wavelengths that probe different phases of the gas. And so a couple of years ago, I looked at this galaxy, ESO blah blah. So this is the velocity map of the tail. As you can see here, you actually see some large-scale coherent motion pretty obviously, right? There's a rotation there. This is more red here, more blue there. Well, duh, because the galaxy that's being stripped is a disk galaxy like our Milky Way. It's rotating. So of course, the stuff that comes out should be rotating. But we can remove the rotation and just look at the residual velocities. And so my collaborators modeled the rotation, removed the rotation. That's also an interesting study. The rotation actually gradually declines and disappears as you move further down the stream. And we can remove that and just look at the residual velocities, right? And that looks kind of like turbulence, right? And you do expect this gas to be turbulent for many reasons. One, this is stripped ISM. I remember when I talked about this work a long time ago, when I had the preliminary results, Romain Tessier was here. He's like, how do you know it's not frozen in ISM turbulence? He's not here today, but I can show him it's not. But he's right that you would expect some turbulence just from the frozen in ISM turbulence. And as the gas rubs against the hot ICM, the shear should also cause Kelvin-Helmholtz instabilities to develop, and that can also give you turbulence. And if the cool clouds become co-moving with the hot plasma, as I mentioned way earlier, the ICM should be turbulent from structure formation, and the cool clouds might start to inherit the ICM turbulence, right? So there are many reasons why this gas should be turbulent. I wanted to know why it's turbulent. So, and that's just a demonstration of Kelvin-Helmholtz instability that my wonderful student Roy is studying. Hi, Roy. Okay, so what I did was I used a moving window and computed the structure function along this window. What I see is it does start with ISM turbulence within the galaxy. And that blue line is Larson's relation. So we're detecting Larson's relation in this galaxy, which is cool on its own. But this quickly grows, right? And saturates at some point. And based on my back on the envelope calculation, the growth and saturation, the growth amplitude, growth time, are consistent with what you would expect from the growth and saturation of Kelvin-Helmholtz instability for a magnetized plasma. But that's not even the coolest part. The coolest part is that is the Coulomb mean free path of the plasma. This whole thing is below the mean free path where the plasma is no longer technically collisional, and yet it behaves like a fluid. So we can just play the same game that other people play with, you always normalize everything with Spitzer viscosity, even though we know that that shouldn't be the description, but whatever. We can say that the effective viscosity must be suppressed at least to the level of 0.01% of Spitzer in order for us to see the turbulence on those scales, because the particles should not be colliding with each other anymore. We don't know why. They still look like they're colliding with each other. Or in other words, the plasma is still effectively collisional on those scales where the particles are not directly interacting with each other. So they must be interacting somehow effectively, probably through the interactions with magnetic fields. And if you ask a plasma person, they'll say it's the plasma instabilities. But the plasma instabilities predicts a Brzezinski viscosity. And oh, by the way, real observers have also looked at more jellyfish tails and confirmed the results in more tails. Brzezinski viscosity would suggest a level of suppression compared with Spitzer on the order of a few percent. And what we showed is effective viscosity is even lower than that. So it's not Brzezinski, it's lower than Brzezinski. So I'm going to read off what I wrote here because I don't fully understand it. But based on what I've read, it means immutability from self-organization could be important. And I'll leave it there, but please help me understand this thing. Okay, so here is my summary and wish list. Black is summary, red is my wish list, okay? Take notes, theorists. Okay, so first, I think we've shown that stars retain some memories of the conditions before their birth, and they can be used to trace as some turbulence. But I still don't know how reliable they are as a tracer and how special they are as a tracer. And we found stellar motions are perpendicular to the local field lines. We have no idea why, so help us. And in clusters, I think I've shown you that cool clouds can be used to trace the motions of the hot plasma, which is hard to observe directly. And the cool clouds can provide valuable insights into plasma properties. But we do need to have a better understanding of the cool-hot phase coupling. And that's something theorists can work on. We detected non-Kolmogorov turbulence in cluster centers, and it has important implications in terms of how AGN feedback operates. But we still don't really know, or people don't agree on how we explain the non-Kolmogorov turbulence we detect. And lastly, the motions of jellyfish tails suggest that isotropic viscosity of the plasma is suppressed to lower than 0.01 spatial value and lower than Berginsky viscosity. And I think it's really time for us to think about how we can properly describe viscosity in these environments and how we properly model viscosity in these state-of-the-art simulations that already resolve the Coulomb free path. Thank you.
Great, thank you so much. We have time for some questions. Yes.
So for all these velocity structure functions, for all these one computed from like filament and also the young stars, have you ever tried higher order structure functions?
Yes. For the stars, it's in the appendix of the paper, I believe. For the filaments, there's a reason why I didn't even put them in the appendix. There might be other groups that, actually there are other groups that published higher order structure functions. The reason why I did not is because here we're looking at projected information, and there is a projection effect. And that is simply, from two clouds that are well separated in the real physical space, but look close to each other in projection. And that is really going to boost your power on small scale. So in a way, this is already flatter than the true slope. And as you can imagine, this is basically giving you a wing of the Gaussian distribution, and that's going to mess up with your higher order structure functions even more. That's the reason why I didn't show them, but I have looked at them. They look reasonably well behaved, meaning they sort of have the slopes that you would expect based on the lower order structure functions. Mm-hmm.
Thank you.
Hi, Mordecai.
So I guess I have two related questions.
Mm-hmm.
Back in Shira et al., something like 2019, we looked at structure functions of collapsing molecular cloud and found that the small lags tended to get more and more power during the collapse. So that would suggest that stars that came out would still have a lot of that small scale power. And then the second more methodological question is, have you tried out extended self-similarity, looking at higher order structure functions and their relationships dividing by the order 3 structure function?
Yeah, someone already asked about higher order structure functions. For the stars, I think in the first paper, we had the higher order structure functions in the appendix. They look really well behaved from what I remember. Yeah, because this is actually pretty close to Kolmogorov, and I remember the higher order structure functions were pretty much what you would expect. And is this small scale power? Is that from, sorry, you said you looked at the stars and there's like small scale power.
We looked at the collapsing molecular cloud and looked at the structure function of the gas.
I see. And there's like basically.
It wasn't Kolmogorov, but because gravitational collapse was dominating.
Yeah. Yeah, I don't know. So we do see effectively, right? So this flattening on small scales can be inferred as a enhanced power on small scales.
Yes.
So but we've already identified like 3-5 things that could boost this. So what you said could be another thing. I have no idea how we could distinguish between these different effects. They will all effectively boost the power on small scales. Yeah, but I should take a look at your paper. Sure. Can you send it to me, please?
I will.
Thank you.
And also similar questions. Have you ever computed like the density structure function or other properties? Well, primarily maybe the density structure function for the filaments and also for the stars, the number density of these young stars. And how compact all these young stars gathered together.
I'm not sure how we would do it for the stars. So in the ISM community, people do look at both the column density structure function and the inferred density structure function. There's the big power law of the sky, right? And that's like a really beautiful power law that covers, I don't know, 7-8 orders of magnitude or maybe even more. For the filaments, great question. We're actually looking at it right now. So not really density structure function, but I guess flux autocorrelation function. Yeah, I'm not sure. I've looked at it in the past and didn't see anything that was obviously meaningful to me, but now there is another student who's actually going to be a pre-doc fellow here, and he's interested in looking at that. So we're looking at it more, and I'm still having a hard time pulling meanings out of the results, but I'll think more about it. And in a way, the surface brightness fluctuation analysis is, my understanding is it's effectively a density structure function, more or less.
Okay, that's my question. So you said that you'd tell Roman why it wasn't ISM turbulence baked in, but can I like see in the velocity structure function, or how do I see that it's not ISM turbulence baked?
Sorry, so the first frame more or less covers just the galaxy itself, and the structure function is this first line.
Yeah,
and that's basically sitting on top of Larson's relation. And so that is the ISM turbulence here, okay? But then as you move down the tail, you see a growth in the amplitude, which means what you see in the tail is not dominated by this anymore. This is very much subdominate.
Okay.
Yeah.
And why is it growing so like monotonically as you
You tell me, you ran all the simulations. That's why I've been asking you.
Okay.
Yeah. So, like I said, I only have very hand-wavy calculations based on these highly idealized stream simulations that at some growth of Kelvin-Helmholtz stability for like single streams. I had to make up some number. I made up some numbers for like the typical width of these things. I mean, what do you say is the typical width of these things, right? Like individual streams. I quoted a number from the observers' papers, but no, I think my back on the envelope calculation is only good like in terms of outer magnitude estimation. So it'd be great to check in a more realistic full galaxy scale simulation that perhaps you have.
Yeah, well, but Nina did it, you didn't like it.
No, I didn't look like this from what I remember. But you didn't have.
Okay.
Yeah, you used AMR. You just have to like resolve everything, all the phases, so that you don't kill the cascade in the hot phase right away. That's my theory, but like I don't have the computing time for you. So someone else, you do. You do. You here. Just burn some more time. Burn some more time and right. Full box.
Force
right?
resolution.
Yes.
Okay, sounds good. Okay. Thanks.
Thank you.
Okay. If there's no other questions, let's thank Yuan again.